Okay, let's start. It's my pleasure to introduce Professor Zbigniew Jelon from CIMPA, Poland. Today is the last day of our mini course, Lipschitz geometry. The idea was to present in the last day something about the ambient Lipschitz equivalence. Then the first class is about existence of such embeddings of Lipschitz mapping, and Professor Jelonek is in charge to do that. Please, Jelonek.
Okay, thank you very much for this nice introduction. And I would like to say a few words about our common paper with Lev Bilbray, Alex Fernandez, and me about the extension of bi-Lipschitz mappings. Unfortunately, I am not in São Carlos for some reasons. I regret, but I have a possibility anyway to give this lecture. I will start, yes. And in modern Lipschitz geometry of I'm sorry because it's impossible to me to do some pictures, but I try to explain some pictures by words. Maybe it's not so good, but I will try. Okay. In modern Lipschitz geometry of singularities, there are two natural metric and three natural classification problems. A semi-algebraic or algebraic subset can be equipped with inner metric, or in other words, the length metric, defined as minimal length of a path connecting two points. You know this notion very good here, yes, in Brazil. Or with outer metric, where the distance is defined simply is induced from the ambient space. Okay, and one can define the Lipschitz inner equivalence, Lipschitz outer equivalence, and Lipschitz ambient equivalence. Two sets are called Lipschitz inner equivalent if there exists a bi-Lipschitz map between the two sets with respect to the inner metric. Yes, the sets are called Lipschitz, and for us, this notion is the most important here in this paper. The sets are called Lipschitz outer equivalent if there exists a bi-Lipschitz map with respect to the outer metric. Yes. Finally, the sets are called ambient Lipschitz equivalent if there exists a bi-Lipschitz map with respect to the outer metric that can be extended as a bi-Lipschitz map to the ambient space. Okay, this means that it has these two sets are embedded in the same way in the Euclidean space with respect to the bi-Lipschitz geometry. Yes. The relation between the inner and the outer metrics are very well investigated, and the theory of Lipschitz normally embedded sets is on the rapid development. See, for example, the works of Misev, Pichon, Kerner, Pedersen, Ruas, Birbrar, and so on and so on. Yes. Our work is devoted to the relations between the outer equivalence relation and the ambient equivalence relation. Yes, we would like to investigate the problem when it's enough to know that two sets are bi-Lipschitz equivalent, to know that they are automatically ambient bi-Lipschitz equivalent. Yes. A recent work of Neumann Pichon showed that even in the case of germs of complex surfaces, the outer Lipschitz equivalence does not imply the ambient topological equivalence. And also there are in the real case the papers of Lev, Birbrar, and Gabrielov, which also show the same. Yes, it is very important, these exams. Professor Birbrar explained these exams in the next lecture. And exams of Birbrar and Gabrielov shows that our theory, which is developed in this paper, is optimal in some sense. Yes. Okay. One of very basic exams in the paper showed that two compact curves in the plane can be outer Lipschitz equivalent, ambient topologically equivalent, but not ambient Lipschitz equivalent. And here I would like to use a picture. It would be the best solution. However, I have no pictures, and simply the idea is the following. Let's imagine the circle and two cusps which are glued to these circles. in this way that outside is one cusp and inside is another cusp, and this cusp has different order of tangency at the singularity, yes, and then do the same in the converse way. The first cusp is inside and the second cusp is outside, yes. And now using the Jordan theorem, it's easy to show that these two one-dimensional semi-algebraic sets satisfy all these conditions. Yes, simply it cannot be if there exists the ambient mapping which extends this by Lipschitz equivalence, then of course they must transform in interior of the circle to the interior of the circle. And since the order of tangency of these two cusps are different, it is not possible. I'm sorry that I have no pictures, because of course pictures is the nicer method to explain this. Okay, and now I go back to these exams of Birber and Gabrielov. These exams show that for gems of real surfaces, the outer Lipschitz equivalence considered together with ambient topological equivalence don't imply ambient Lipschitz equivalence. In fact, Birber and Gabrielov have constructed the gems of surfaces in dimension 3 and 4, yes, left, yes, 3 and 4, which have these properties, and this means that our theorems, which I will state in this paper, are optimal. Yes, they cannot be improved, because we show that in the case of gems in dimension 5, or all real gems are, or even complex gems in complex dimension 5 are ambient Lipschitz equivalent. Okay, and now we have the following fundamental problem, which is very strange that this was not solved up to our paper. Yes, given a semi-algebraic set X of dimension k, how one can estimate in terms of k the dimension of the space Rm such that there exists a bi-Lipschitz embedding of X into Rm, and we prove the following Whitney type theorem for bi-Lipschitz category. Yes, this is very nice theorem and very natural in some sense. How it's surprising that it is so easy. Yes, let X be a closed semi-algebraic set of dimension k with the induced metric. Then there exists bi-Lipschitz and semi-algebraic embedding fx to R2k plus 1. Hence, this R2k plus 1 is the optimal number. Moreover, if X is an algebraic variety, then we can assume that fx is also an algebraic variety. And in this theorem, we see some very surprising and general principle, namely the category of semi-algebraic sets with bi-Lipschitz mapping, with bi-Lipschitz semi-algebraic mappings, behaves more or less as category of smooth manifolds with smooth mappings. And all, for example, Whitney theorem for smooth, in smooth case, looks more or less in the same way. Yes, maybe it's something deeper here. We give also a complex version of this theorem, namely we have the following theorem: any compact semi-algebraic, yes, another result of this type. I formulate this complex version later. Okay, it looks very similar. Any compact semi-algebraic set X of dimension k is bi-Lipschitz equivalent with respect to the inner metric to a Lipschitz normally embedded semi-algebraic set Y, which is a subset of R2k plus 1. And this is some improvement of Birber and Mostowski theorem. In fact, Birber and Mostowski proved this theorem this theorem without this restriction that y can be embedded in R2k plus 1. However, using our methods, it's easy to reduce the Birber-Mostowski theorem to this form. Yes. We simply use some projection, some generic projection. Okay. When the outer Lipschitz equivalence implies ambient Lipschitz equivalence, in general, 2 by Lipschitz, there is a question, of course, it should be. In general, 2 by Lipschitz embeddings into R2k plus 1 are not ambient equivalent. And here we can mention these examples, for example, of Birber or very nice examples of Sampaio, which is an example of a curve which can be embedded topologically in R2. However, it cannot be embedded in bi-Lipschitz way in R2. I'm sorry, I have no pictures here. That's better to, but it's very nice construction. Simply, it uses the fact that if you have two arcs which has the same orders of tangency at some point x, then any other curves which is between them must have also be tangent to both of them. And using this, we can simple observation, we can construct such an example. We say that a semi-algebraic set X admits a unique embeddings to Rn if for any unique by Lipschitz embedding to Rn. If for any 2 by Lipschitz embeddings Fg X to Rn, where Fx, Gx are semi-algebraic sets, there is a by Lipschitz homomorphism of Rn such that the following diagram, we have this equality. G is simply a composition F composed with P. This means simply that Fx, Gx are embedded in the same way in the Euclidean space with respect to the by Lipschitz group. We cannot distinguish them. No, it's here. In other words, the subset X in Rn has a unique embedding into Rn if any other semi-algebraic subset Y in Rn which is equivalent to X with respect to the outer metric is ambient Lipschitz equivalent to X automatically. And now using this Whitney theorem for in by Lipschitz category, we can modify algebraic methods developed in Jelonek, Kaliman, Srinivas to the Lipschitz category, and we obtain very nice result. To state this result, I can first define tame by Lipschitz homomorphism. Namely, tame by Lipschitz homomorphism is a mapping of this type, yes, phi Rn, where P is Lipschitz mappings. Yes, it's easy to see that such a mapping is by Lipschitz. It's very easy. Yes, here this P depends only on first n-1 variables. Yes, it's easy to see that the inverse here has a minus. Yes, and it is by Lipschitz. Very easy. Yes. Note that such a mapping has almost everywhere Jacobian equal to 1, hence it preserves the n-dimensional volume of Rn. Yes, that our bonus is that our mapping additionally preserves volume, Lebesgue volume in Rn. Okay, this is also interesting. And now I formulate our main result. Of course, later I try to explain the proof of this result. Yes. Hello, do you hear me? Hello. Lev, Alex. What's happening? Hello? Do you hear me? What's happening? Okay, okay, I'm sorry. I see that you can hear me. Okay, I'm sorry. Let X be a closed semi-algebraic subset of Rn of dimension k. Let Fx to Rn be a semi-algebraic and bi-Lipschitz embedding. If n is greater or equal to 2k plus 2, then there exists a tame bi-Lipschitz and semi-algebraic homomorphism Frn to Rn such that the restriction F to X is simply the mapping F. Moreover, we have the following isotopy. There is a continuous semi-algebraic family of tame bi-Lipschitz semi-algebraic homomorphism such that F0 is identity and F1 X is F. Here is interesting because this family, you see, you start from identity and then the Lipschitz constant near 0 is very close to 1, yes? And maybe there is a possibility to use some results like Comte results to say something about real version of Zariski conjecture. Yes, I don't know, but it's interesting here that we have such a isotopy of bi-Lipschitz mappings. And corollary, let X be a closed semi-algebraic set of dimension k. If n is greater or equal to 2k plus 2, then X has a unique semi-algebraic and bi-Lipschitz embedding into Rn, up to a semi-algebraic and bi-Lipschitz tame homomorphism of Rn. Using slightly more subtle methods, in the local case, we obtain better local results. The analog of theorem 3.3 is the following. Let X0 be a germ of a closed semi-algebraic set of dimension k, then there is a bi-Lipschitz semi-algebraic embedding of X0 into R to K0. Okay, and also we have analog of this main result. Let X0 be a germ of closed complex algebraic affine. I'm sorry, this is a complex version of these results. Yes. Then there is a bi-Lipschitz and regular embedding of X0 to C2K0, such that Fx0 is a germ of complex algebraic variety. And this theorem generalizes a result of Tessier. Tessier proved this theorem for k equal 1. And we have also the following version for germs of our main theorem. Let X0 be a germ of a closed semi-algebraic subset of Rn0 of dimension k. Let Fx0 to Rn0 be a semi-algebraic and bi-Lipschitz embedding. If n is greater or equal to 2k plus 1, then there exists a germ of tame bi-Lipschitz and semi-algebraic homomorphism such that F restricted to X is F. And also there exists isotopy. And as you compare this theorem with results of Birbrar and Gabrilov, you see that this theorem is optimal. You cannot improve this. And also, let X0 be a germ of closed semi-algebraic set of dimension k. If n is greater or equal to 2k plus 1, then X has a unique semi-algebraic and bi-Lipschitz embedding into Rn0, up to a germ of semi-algebraic and bi-Lipschitz tame homomorphism of Rn0. Okay. And the last result, let X and Y0 be germs of one-dimensional semi-algebraic subset of R2. If X0 and Y0 are outer bi-Lipschitz equivalent, then they are ambient bi-Lipschitz equivalent. This is some extra results which works only in dimension 1. Yes, in higher dimension there is no analogical results. No, as I replaced for surfaces, situation is more complicated. There are germs of surfaces x0 and y0 in Rn, where n is equal to 3 or n equal 4, and a semi-algebraic bi-Lipschitz mapping, which can be extended to homomorphism of Rn, but it cannot be extended to a bi-Lipschitz homomorphism of Rn0. This means that our results is optimal. And now I have some time, I don't know, I try to sketch some our methods, yes? In this paper, we consider the Lipschitz category L. Its objects are closed subset of Rn, mainly semi-algebraic, equipped with the outer metric, and morphisms are Lipschitz mappings with respect to the outer metric. Okay? We also consider the Lipschitz semi-algebraic category. Its objects are closed semi-algebraic. Mainly, we consider this category, LS. It is the most interesting, in fact. Its objects are closed semi-algebraic subset of Rn and semi-algebraic mappings, and by Lipschitz semi-algebraic mappings. Yes, we start with the following basic definition. Maybe I give it. Okay. Let X be closed semi-algebraic subset of Rn and Fx Rn be a Lipschitz mapping. We say that F is a bi-Lipschitz semi-algebraic embedding if the mapping Fx to Y is a bi-Lipschitz, and F and F minus 1. This means F and F minus 1 are Lipschitz semi-algebraic mappings. Yeah? Okay. Maybe I skip this. Let X be a closed subset of Rn. We will denote it by Vx, the vector space. Now I would like to construct the sum functor, yes, from the category of topological spaces to the category of vector spaces. Let X be a closed subset of Rn. We will denote by Vx the vector space of all Lipschitz function on X. Of course, it is a vector space. Yes, if Fx to Y is a Lipschitz mapping of closed sets, then we have the natural homomorphism, yes? Because the composition of two Lipschitz mapping is again Lipschitz, then we have a functor, yes? Contravariant functor, in fact. If X is a closed semi-algebraic subset, then by analogy, Vs will denote the vector space of all Lipschitz and semi-algebraic functions on X. And now we have the following fundamental proposition, which is, since every Lipschitz function on X is the restriction of some Lipschitz function on Rn, we have that the mapping iota star from Vrn to Vx is epimorphism. It's very easy, yes, because we take Lipschitz function on X, we can extend this to the global function on Rn, and this means that this mapping is epimorphism. Yes. In fact, it is only one, in principle, maybe not exactly one, but in principle only one place when we use properties of Lipschitz function. Yes, the rest of this paper is geometry, and here the fact that the function is Lipschitz is encoded here. Yes, in this theorem. Yes, in this proposition. Let X Rn be a closed subset and Fx Rn be a Lipschitz mapping. The following conditions are equivalent. F is a bi-Lipschitz embedding, and the induced mapping Vf from Vrn to Vx is an epimorphism. Yes, then we encoded the notion of bi-Lipschitz embedding simply to some algebraic notion. Yes, which is very, very useful for us. Of course, the same result holds in the category LS with the same proof you have here. Yes. Okay. And now we have the following lemma, which is let X be a closed subset of Rn. Assume that the projection X to RL cross 0 is a bi-Lipschitz embedding. Then there exists a tame bi-Lipschitz homomorphism P Rn to Rn such that Px equal to P. And now, in fact, I need to explain this. I need some piece of paper. But what is the idea of this? Namely, you see, in fact, this mapping from X to RL is an embedding, and this means, in fact, that we have epimorphism from RL to from VRL to Vx. Yes. In particular, every function xk from k greater than L is simply can be wrote as xk is p from x1 xl. Yes, xk is pk from this variant. No, but this is, and of course, xk minus pk is 0 on x. Yes, and now consider the function x1 xl and xk plus 1 minus pk plus 1 xk plus xl plus 2 minus pl plus 2, and so on, xn minus pn. Yes, this function is of course tame by Lipschitz mapping, and now on x, but you note on x all x k minus pk are 0. That on x it coincides with this projection. This is algebraic trick. Yes, simple algebraic trick which uses the fact that this mapping is epimorphism. Okay, and similarly, we have the following version of the Whitney-embedding theorem. Let X be a closed semi-algebraic set of Rn of dimension k. If n greater or 2k plus 1, then there exists a system of coordinates x1, xn, such that the projection x to x1, x2, k plus 1 is a by Lipschitz embedding. Moreover, if x is an algebraic variety, then we can assume that px is also an algebraic variety. And the method is very similar as I explained before. Yes, simply we take a projection from the point which is disjoint from the second locus of x. It can be done, yes, and then by simple computation we see that it is okay. Okay. And a direct consequence of Whitney lemma is the following, this Whitney theorem. Let X, Whitney theorem in semi-algebraic category. Let X be a closed semi-algebraic set of dimension k with the induced metric. Then there is a by Lipschitz and semi-algebraic embedding fx to R2k plus 1. Moreover, if X is an algebraic variety, then we can assume that fx is also an algebraic variety. Now, in fact, we use several times this lemma, yes, this Whitney lemma, which on other sides follow from this simple geometry, yes. This result is sharp. In general, you cannot embed it a semi-algebraic curve in a by Lipschitz way into R2, even if there is no topological abstraction to do it. And indeed, we have this example of Sampaio, which I explained at the beginning of my lecture, yes. And here we have this generalization of Birber-Mostowski theorem, yes, as I explained, yes. Simply, if we use sufficiently general projection, then by the previous lemmas, this mapping, the image of Birber-Mostowski variety again has the same properties, but it is contained in smaller spaces. Yes, because phi preserves the equivalence of the inner metric and the outer metric. Yes, such a embedding, such a bi-Lipschitz mapping. Yes, preserves this. Okay, and maybe I skip which I have time. Maybe I skip this. Maybe. And I would like to say a few words about the proof of the Manhã theorem. And in fact, we have to understand what in fact it is. What does it mean by Lipschitz projection? Yes, what does it mean by Lipschitz projection? In fact, by Lipschitz projection can be explained using only geometric terms. Yes, not we can forget about metrics. We can use only the language of geometry. And in fact, here, what is projection? If we see on the affine projection, but from the projective point of view, then every projection has a center LS, yes, and it can be defined in this way, yes, that we have Rn is the set of proper points of projective space of finite points, yes, and every x is we take the linear space, projective linear space, which is generated by the center of the projection and x, yes, and we cut this with some linear space, yes, and this is a projection. Yes, every projection can be defined in this way. Yes, and here is the basic lemma which explain the geometry of bi-Lipschitz projection. Let X be a closed subset of Rn, denoted by lambda, which is contained in the hyperplane at infinity, the set of direction of all seconds of X. And let sigma be the closure of this set, yes, where P infinity is a hyperplane at infinity, and we consider the projective closure, yes. Let PL be a projection with center L, then PLX is a bi-Lipschitz embedding if and only if the set L is disjoint from sigma, yes. This means that the sets of the closure of the direction of seconds of X can be disjoint from the center of the projection. This is if and only if condition for the mapping for the projection to be bi-Lipschitz. Yes, this is very geometric picture. Yes, it's only geometry here, and it is even better than in other categories because, for example, similar theorems are also holds in smooth category. However, we cannot there if and only if condition. Yes. And in bi-Lipschitz category, we have if and only if condition. This is simply, this method using projective geometry is simply created by God for bi-Lipschitz category. This is exactly works here. And here we have also lemma, let X be a closed set and let be a Lipschitz mapping. Let Y be a graph of F, then the natural mapping from X to the graph of F is a bi-Lipschitz embedding. It's easy to check this. Oh, this proof is, but it is not very interesting, yes, because every student can compute this. Yes, it's very easy. And now we have the fundamental lemma. And for the proof of the lemma, it is wonderful that this if and only if condition works here in the beautiful way. This is and makes this proof very easy, in fact, of this lemma. Let X to Rn be a closed semi-algebraic set of dimension k and n greater or equal to 2k plus 1. Assume that the mappings P1 xy to x and P2 xy to y are bi-Lipschitz embeddings. Then there exists linear isomorphism St of Rn with determinant equals 1, such that if we change coordinates in Rn by S and we change coordinates in the second copy of Rn by T, then all projection Z1, Zn1 zw to z1 zr vr plus 1 vn are by Lipschitz embedding. Here is very important that the number of variables here is n plus 1. Is n, I'm sorry, is n, is exactly n. And the method of this is very, in fact, in some fact, very easy, because what does it mean that this mapping is a projection, yes? The by Lipschitz projection. This means if you consider this as if you consider the graph of this, yes, the graph of this mapping, this means simply that if you cut this graph by x1, xn, then the dimension of this must decreases. The dimension of the points of the graph at infinity with cutting by x1 and so on might decreases by 1 and so on. If you take a sufficiently linear combination of this x1 and xn, we are sure that this intersection must decreases at least by 1, because otherwise we constructed a point which belongs to some seconds and to the center of the projection. Yes, because it simply means that it is, because we know simply that the center of the projection, say x1 equals 0, xn equals 0, omit the closure of the graph at infinity. Yes. And if we use several times this construction, we can construct these good variables. Of course, it is maybe slightly more complicated, but this is the main idea. And now, if we have this, in fact, we have this theorem. Again, I would like to explain this if I have some piece of paper. It is also some algebraic trick. And in fact, it is the same algebraic methods when, for example, I used several years ago in algebraic category. Yes, that in fact the methods is more purely algebraic. It's nothing more. Yes, we reduced the proof simply to algebra. Okay. I'm sorry, I have no contact. In fact, I explained these more important things, and I see probably my time is finished. Yes. However, I have no contact with anybody. Yes. I don't know what I have to do now. I can finish here because I have no pictures, and the rest, in fact, it was my. I would like to give some pictures and explain by pictures. Hello?
Hello. So
yes.
let's take the speaker, please.
Okay.
So questions?
I'm sorry, because I was prepared for the slightly different form of this lecture, and because
Sorry. So there is a question in YouTube chat.
okay.
Is that a Lipschitz analog of uniqueness of normalization?
Uniqueness of normalization. No, in some fact, you know, in by Lipschitz category, uniqueness of no, it's. In fact, normalization is a property of the set, yes? And here we have uniqueness of the embedding, yes? That is probably is more closer is to say that every smooth variety has only one embedding into R2K plus 2, yes? This is analog, yes?
So, more questions?
Hi. Thank you, Zygmunt, for the nice talk. So is it possible to maybe to look at the set of singular projections in order to understand the different types of embeddings in our 2K or 2K plus 1, right?
Yes, yes. Of course, of course. Good embeddings, good embeddings gives by Lipschitz mappings. Yes. That if you would like to obtain something different, you have to use these bad embeddings. Yes, the bad projections.
Yeah. And
No,
look
but
at, yeah. Okay, thank you.
thank you. And
More questions? So I have one question. It's
yes.
big. In order to generalize the Whitney type theorem, is it possible to take the hypothesis of the set? I mean, we don't assume the set is semi-algebraic. We only assume this is stratified.
I don't.
K-dimensional stratified set.
No. Probably it works also. Yes, if it's. In fact, we have to control the set of seconds. If we control the dimension of the set of seconds, it's okay.
I see.
If the dimension of the set of seconds at infinity is small, that is okay. The only bad situation is that the seconds fill all the space, yes? The whole space at infinity are then subset.
I'm wondering about the Vaisala, the Finnish mathematician, Vaisala conjecture. You know this conjecture.
Could you recall it?
Vaisala
Conjecture?
conjecture. Suppose you have a Lipschitz manifold with dimension n. The conjecture is it's possible to embed this Lipschitz manifold in R to n plus 1.
If this manifold has some good stratification, as you mentioned, but what does it mean, good stratification? That in some sense we control these seconds, yes? For example, this stratification has some. No, we have to discuss, Alex. It's good question. It's good question. Maybe it's for our future project problem. Yes.
Thank you, Zbigniew. So let's thank the speaker.
Thank you very much.
You resume in 5 minutes. Okay.
Oi.
So now let's start with the last lecture of our mini course. This lecture is about metric nodes. Metric nodes are obstruction to Lipschitz embedding. So the speaker is Professor Lev Bibrahi from UFC. And so, Professor Lev, it's your turn now.
Thank you for presentation, Alexandre. So that I prefer to have some contact with the audience, but since this guy from the technical support don't provide these, so that I suppose that nobody will ask me questions, right? Excellent. So then I would like to talk about the metric nodes. It's just, let's say, the general and somehow just natural continuation of the talk of Zbigniew. So let's start from the following, that if you have a semi-algebraic surface or just any kind of semi-algebraic setting R to the n, then what do we have? We have two natural metrics, as Zbigniew was saying, as probably it was said also in the talks of Edson and the talk of Alexandre. We have this inner metric. This is the length of the minimal path connecting two sets. Then we have outer metric, and then we have the notion of normally embedding that was, or LNE, that was discussed here before. So then what we have this somehow the two natural metrics, and then we have three natural classification problems in the Lipschitz geometry, that we have inner Lipschitz equivalence, we have outer Lipschitz equivalence, and we have the ambient Lipschitz equivalence. So then we have these three natural equivalence relations, and our goal and what we are looking for is just the relations between these ambient, outer, and inner. So then in this talk, I will speak more about ambient, but then in the end of the talk, if I will have sufficient time, then I will come back to the outer classification and will explain what actually happens over there for this kind of outer Lipschitz classification. Okay, then for the moment, what about ambient and outer? And it was mentioned probably in the beginning of this course that what about the inner equivalence? Then we have a beta horn. And actually, if you have isolated singularity, then with respect to the inner Lipschitz equivalence, any germ of a surface with isolated singularity is by Lipschitz equivalent to the beta horn, and the beta horn is not supposed to be normally embedded. Actually, you see that you have a picture E, where it's just a revolution surface of the cusp, and we have picture B, where we have that somehow just a pair of arcs that have different order of contact between them than in the picture E. So that it means that if you are not normally embedded, then really the outer and the inner equivalence, they are not equivalent. And then you see that in this picture, you see the case where the two surfaces are inner by Lipschitz equivalent and not outer by Lipschitz equivalence. I'm sorry if I'm repeating this, that was actually mentioned several times. So this is, let's say, the difficulty of outer and inner. And then we have the Horn theorem in the inner equivalence. We have that a semi-algebraic surface is with isolated singularity is always inner by Lipschitz equivalent to a beta Horn for some beta, right? For instance, a germ of an irreducible complex curve is inner by Lipschitz equivalent to the germ of a complex line, right? And then there is an interesting, and it was actually the theorem of Tessier, and then theorem of Alexandre Fernandez, that in slightly better form than the theorem of Tessier. And then there is a sort of just extension of that by Neumann and Pichon, saying that if you have two germs of irreducible complex curves in C2, then the ambient Lipschitz equivalent is equivalent to the outer Lipschitz equivalent, to the outer Lipschitz equivalence. So these are the situations that were known before the, let's say, sufficiently rapid development of this kind of relations between these two, actually between these three classifications, right? So then let's start from the ambient geometry, and let us speak about the first invariant that was actually several times described by Professor Fernandez and Professor Sampaio, the tangent cone. So here is the definition, and the limit here means the Hausdorff limit, right? So we just take the intersections of our set with sufficiently small spheres, and then we just normalize them, taking this 1 over epsilon, and then just take the limit of these when epsilon tends to 0, and then take a cone over that. And this is the tangent cone. This is the tangent cone. And the theorem of Sampaio that Edson explained was that, and this is the first nice invariant, that if you have two ambient or outer Lipschitz equivalent germs of semi-algebraic sets, then the tangent cones are outer or ambient Lipschitz equivalent. So in other sense, in the other words, the tangent cone is outer and ambient by Lipschitz invariant. So, and then the tangent cone helps to answer to give a negative answer to the following problem. Does outer Lipschitz equivalence implies ambient Lipschitz equivalence? Just let me notice one point, that actually when we consider the ambient Lipschitz equivalence, of course we can make plenty of examples of the things who are outer by Lipschitz equivalent and not ambient equivalence if they are not ambient topologically equivalent. Just take knots in S to the 3 and take cones of these knots. That's it. Or, okay, even knots themselves. because the topology brings you just natural abstraction of the elliptic geometry, and then we must suppose that there are no topological abstractions, so that all the theory of the ambient elliptic geometry should be done in the case that we have no topological abstraction. Okay, so that this is a point. So we shouldn't have topological abstraction. We have just only ambient. So we always will suppose that our sets are ambient topologically equivalent. Okay, and then let's start from the first examples. And here there are examples in R⁴. This is the joint work with Andrei Gabrielov. The examples, just point one, do I draw here? That it's the only, the usual question of several people when I make the exposition, then what is mean? That these are surfaces, right? These are not curves. You see curves, but I mean surfaces. That what we draw a link. We draw the link with the, and here when I just put some points, the points mean curves. So that this is a dynamical picture. This is the dynamical picture. And what do we see from the dynamics? We see that here the curves gamma plus and gamma minus, when they go to the singular point, then they just have an order of contact, so that they actually go together and they tend one to another faster than linearly. And here we suppose that the rest, the rest is going to the singular point with the linear rate, with the linear velocity. And then we consider these points and these points. When we want to see the tangent cone, just you suppose that gamma, you identify gamma plus and gamma minus, psi plus and psi minus, gamma plus here, and gamma plus and gamma minus here, and psi plus and psi minus here. Then when we identify them, then we see the pictures of the tangent cone. So we suppose that everything turned to zero conically, and these arcs, they actually tend to each other with some order of context which is bigger than 1. So that when we go there, and just when we identify these pictures, we see that they are even not topologically equivalent, right? So that if we see them in S⁴, because these are examples in R⁴, and then if we just go to the picture, we see them as links, as somehow as singular curves in S⁴, in two-dimensional sphere. And these two guys in two-dimensional sphere are not even not ambient topologically equivalent. And then if the tangent cone are not ambient topologically equivalent, they are not ambient Lipschitz equivalent, and that is why because of the CIMPA theorem, the previous slide, then because of the CIMPA theorem, the corresponding surfaces are not ambient Lipschitz equivalent, because the tangent cones are not ambient topologically equivalent. Okay? I would ask if there are some questions, but what? And then there is this extremely qualified, extremely competent person from the technical support that just somehow just cut all my my contact to the audience. Okay, very good. And then we go to the we go to the examples in R to the 4, where our links live actually in R to the 3. So that here we see the another kind of examples that they are basically of the same idea as the examples in R to the 3, that here you see the connected sums of the of two three-foil knots, right? And you see the pair of arcs, and then the pair of arcs just they have a contact bigger than one, so that and when we go to the tangent cone, we will see there just the two three-foil knots attached in one point. In here, we see the connected sum of two three-foil knots, and there you see there they are connected some with the trivial knot, right? And then you see that these two things are just ambient topologically equivalent. And since when we go to the tangent cone, we just break everything, and then these two things will be not ambient, the tangent cones will be not ambient topologically equivalent. Okay, very good. Now, just to make another examples, I want to consider so-called bridges. So that what is here in this picture? What is here in this picture? These are special germs of two-dimensional surfaces. So that here you have what do I have in the picture? You see two segments, but they are actually triangles, because this is the link of the triangle, and then we, when we go to the singular point, you see that the triangle this is a beta triangle, that the triangle comes to the singular point with the velocity with the rate beta. And you have the upper triangle, and then you have the boundary, the down triangle, right? There are two of them, and the distance between them have the order q, which is bigger than beta, right? And here we have the so-called broken bridge. Broken bridge we receive in such a way that we just we just cut this area over here, and we just include, so we have just we cut this small triangle, we erase them, and then we cut, then we glue another kind of triangle. So this is a sort of surgery. The sort of surgery that we just make this kind of bridge, that is contained to the surface, and then we just modify this bridge. And this will be the way how to construct more examples. So that just remember that we have this kind of bridge. Okay. And then just you can see just here there two A and B, you have the lengths of two surfaces, right? You have the lengths of two surfaces that they are first outer by Lipschitz equivalent. They are ambient topologically equivalent, but they are not ambient by Lipschitz equivalent. Why? Because here we just have a bridge over here, and then if we break this bridge as it was just designed in this in the previous slide, if we break this bridge, we get a picture C, that if we break the bridge in the picture A, we get the picture C. And if we break the bridge on the picture B, we get the picture D. So these are two surgeries, actually, that in the unique surgery that happens in the bridge, and the surgery bring you a way how to prove that these kinds of links, these kinds of knots are not ambient by Lipschitz equivalent. Because if they were ambient by Lipschitz equivalent, then if we make this kind of surgery, we should obtain something who is ambient by Lipschitz equivalent, and in particular something with that is ambient topologically equivalent. And using this kind of the examples, and you know, we can twist plenty of times, and if we twist plenty of times, we always get different topological types of the nodes. And these kinds of topological types of the nodes, they depend on the number of twists. And this number of twists don't bring you anything in terms of ambient topological equivalence, and bring you nothing in terms of their outer by Lipschitz equivalent. But when we come to the ambient, we come to the ambient by Lipschitz equivalent, they distinguish these kind of surfaces. So then, just to summarize these kinds of examples, I just bring the, just I formulate the theorem joined with Andrei Gabrielov, that for any isotopy type of a real semi-algebraic surface in R⁴, there are infinitely many semi-algebraic surfaces such that first, all the links are isotopic. All the surfaces are outer by Lipschitz equivalent, and all of them are not ambient Lipschitz equivalent. All of them are not ambient Lipschitz equivalent. So this brings you this kind of, not only the answer, the negative answer no, that it brings you the answer to how many no. There are plenty of no's here. So that, and then we decided to just to go further, just to compare this kind of their ambient, the problem of the ambient Lipschitz. By the way, in this picture, you see how do you apply this surgery. If you don't have it before, we have this kind of bridge surgery where we had just a trivial knot. And here when we go over here, we see that this kind of surgery can be applied not only for the trivial knot. Okay, so that even for a given topological type, we can produce infinitely many bi-Lipschitz types. Now, the second question: how big is really this kind of and how rich is this kind of the question of the ambient Lipschitz classification of surfaces? Then actually this, what does it mean, how rich? That if you go to the this kind of classification problems, and then just we can compare one classification problem to another. That, for instance, in this case, we can make the comparison to the knot theory. So that what is this kind of Lipschitz ambient classification in comparison to knot theory? And the next result shows that actually these classification problems contains the knot theory totally. Means that for any knot X, there exists a semi-algebraic surface xk in R to the 4 such that the length of xk at 0 is a trivial knot in S to the 3. Then second, all surfaces xk are outer Lipschitz equivalent. Then xk and xksl are Lipschitz equivalent only if the knots K and L are isotopic. So it means that the knot theory is just embedded in our ambient Lipschitz theory, even in the case that the links are trivial knots. Okay, so here we are, and here is in this picture you can see the idea of the proof. Idea of the proof that let me just briefly explain how to do that. Maybe it will help for the students to read the corresponding papers, because when you will see how we describe this in the papers, you can see that it somehow looks quite formal, but this is what really we do. We have a band. We have a band just over the knot. A band contains just two isotopic knots. And then from the band, we take, now, as usual, we take, this is a picture of the link, right? That we we take, when we go to the singular point, we take a cone. So this is a picture of the link, and in this point you see, in this point you see that here the order of contact is actually bigger than conical, so bigger than one order of contact of these two areas. And then we go to the tangent cone. You see that these two guys just, they coincide, somehow they are attached one to another. Then what really happens? And then our surface is exactly the surface that is a cone over this one, and this one somehow where we make this kind of surgery, right? This is what actually happens. This was actually happens, and why the surface has a trivial knot, because we constructed in such a way that it is it's a boundary of the band. Since it's a boundary of the band, then it's trivial. What do you want? Then this is basically the idea how we came, and we call this universality. And universality means that we universally embed knot theory to our theory, so that it means that the knot theory is embedded to this ambient Lipschitz geometry. And this is the reason why we call this metric knots. Let me go on. So this is another kind of even the actually that if you consider this kind of knot, it's not unique. We can even twist, and if we twist a little bit more, all the time when we make this kind of twisting, we get more and more and more and more and more different surfaces, so that it means that embedding is not just one-to-one, so that even there are much more here than just the knot theory. Well. So I don't explain this kind of, and even, and then there is a theorem, the universality theorem, too, that I actually like myself. I don't know what about you, that if you have this kind of two-knot theorem, that if you have two knots, K and L, then we can construct a germ, XKL, such that the germ, the link, is isotopic to L, but the tangent link is isotopic to K. And for any K and L, all these things are outer by Lipschitz equivalent, but not ambient, of course, because the tangent lengths are different. And this is the picture that we just make a connected sum with a small horn over L. So this is what do we have with the metric knots. And this lecture I gave several times, and there are some possible continuations that I'm somehow waiting for, because then you will probably just somehow there are some questions that what are the conditions when the tangent cone is a good invariant, so that if the given topology or given outer Lipschitz geometry brings you unique or at least finitely many, and when there are finitely many, when there are infinitely many knots, metric knots with this kind of we are working on that, and you will see that there will be slightly more theorems with this kind of things, with this kind of on this kind of work, on this kind of subject of metric knots. But I just make you curious, just to see what's happening, and then of course this is sort of remark for the students that everybody are invited, and who is interested, I just welcome to be a collaborator. And then there is another field that you can contribute, let's say that you can contribute, for instance, just trying to make just a knot theory, just to make knot invariants. We started this slightly with Misha Brandenburski, just adapting a little bit of John's polynomial, but this is a very basic that we could probably contribute more. And let me just say some another things about outer geometry. About outer geometry, then when you know, we started different directions, and once we were doing this kind of pizza paper with Alexandre Fernandez, Vincent Grandjean, and Andrei Gabrielov, then we had a natural question. Suppose we have two normally embedded Hölder triangles. T just is bounded by the arcs gamma 1, gamma 2, and T prime bounded by gamma 1 prime and gamma 2 prime. And suppose that they are normally embedded, right? They are normally embedded, and also this is the condition that the order of contact of the first boundary curve to the second triangle is realized by the contact of the boundary curve with the boundary curve. And the second, that the boundary curve of the second triangle is also realized by the boundary curve. And okay, then what's the question? Is it the case where this pair is by Lipschitz equivalent to the following thing, to the triangle and the graph of the distance function? By the way, if you have just triangles where you have a triangle and the graph of a Lipschitz function, this is exactly the same. That we have this kind of the conditions. But in general, if you have union of normally embedded triangle, is it the equivalent to the graph of the distance function? And then the surprising, even for us, answer that it's not no, but it is a lot of no. So that here there is one of the examples where we have just one normally embedded triangle. As usual, I consider these as what? As the link. So that what I'm drawing is the link. I draw the link. I always draw the link. So what actually happens then? You can see how complicated could be the geometry of the pair, even you know that the triangles themselves are normally embedded. So then, and this will be probably a subject of a lecture that I or Andrei will give slightly later, because really it is somehow just quite complicated and really quite rich subject in the outer geometry, even in the very, very stupid situation where we have just only two triangles. And just when I started my propaganda, let me just also notice that in the outer geometry there is another interesting subject developed by Andrei Gabrielov and Emmanuel Souza. The story about the canonical decompositions of the of some surface into you know that it was actually explained. Then we have a canonical decomposition into normally embedded triangles. Let's say we have a decomposition. In the case that we make inner geometry, we have a decomposition. And what is a canonical decomposition into normally embedded triangles? And this was really developed by André and Emmanuel. And this is another surprising story, that we don't have canonical decompositions into triangles. We have canonical decompositions into zones. You know that there are this kind of normal and abnormal arcs. So we have, we consider the Valette link of our surface. And what is Valette link? That Valette link, actually we make always the pictures of Valette link. The Valette link is the set of the arcs parameterized by the distance to the singular point. And what do we have here? We have the pictures of the Valette links. And so that arc is called abnormal if it is a boundary of two normally embedded triangles such that their union is not normally embedded. And arc is called normal if it is not abnormal. So, and here there are normal and abnormal arcs, so that the red arcs are abnormal, and here you have green normal arcs. And then the result is that in this case we have just a canonical decomposition into the zones of abnormal arcs. And there are four types of abnormal zones, somehow four typical types of abnormal zones. That's a spiral-like. I don't define that. I'm saying that that there is a development, and the development is quite rapid, and there are different directions, and who interests could really join us. And then there is a picture about how that we call snakes and non-snake zones, about how these kinds of abnormal zones can be really obtained. So I guess my time is over. So thank you for your attention.
So, questions?
Hi, Lev. Thank you for your nice talk. I have a question. So, for one isotopy class with respect to the outer equivalence, you may have infinitely many non-ambient equivalent semi-algebraic surface, right?
Yes.
So is this genuine moduli, or if you put a bound on the degree of the semi-algebraic surface, maybe using Mostovsky theorem, you think that we may have finite number? And something else, I mean, and then we can also conclude that we have infinitely many surfaces that are not, that the degree is not preserved under isotopies. Right? I mean, so you may have semi-algebraic surfaces that are isotopic with increasing degree.
Very good question, and I will be extremely happy, because really that if we have the degree, in this case complexity, of course, that the complexity of the links, then the complexity of the links will not permit this kind of so many twists. If they bound complexity, then we cannot make this kind of number of twists. But this is a very interesting direction and absolutely undeveloped. So I will be happy if you will join us with this kind of the consideration. That this is very basic. That that there are some sort of attempts in knot theory that just they consider this kind of the diagram, and if you just limit the number of the intersection of the diagram, how many just non-isotopic knots you can have. This is this kind of question, and but in this kind of metric knot theory, it's totally undeveloped. So thank you for the question.
More question?
Hello.
Can you show the slides again, please?
What?
Can you show the slides again, please?
What slides?
The one where you showed the theorem about irreducible complex curves in situ.
Let me show. Irreducible complex curve in situ. Here we are.
Yeah, this one. If I didn't understand wrong, you are saying in the last statement that having the same Puzo exponents is equivalent to B outer Lipschitz equivalent.
Yes. Outer
Right.
and ambient.
So, but having the same Puzo exponents is equivalent to B topological equivalent curves, right?
Yes. And outer,
So-
in this case, outer equivalent, topological equivalent, and ambient equivalent are the same.
Okay, thank you.
More questions? No. I have one question, Lev.
Yes.
So, do you have any result in the complex setting?
No.
No. No one.
Not a single one. And you are invited to join the complex project.
Everybody here.
And
is
everybody,
invited to do.
everybody are invited for a collaboration.
No
So
question?
if someone has ideas, has any ideas about complex surfaces, then I will be extremely happy to listen to all this and just to work with anyone on this kind of. What I'm doing now, I'm thinking about the real case. But if you will. And really, that there are some kind of, there is a very interesting direction by Marina Ville and Marc Sorer that they consider minimal nodes. And what actually happens in minimal nodes, it's also very curious. I'm very curious about what's happening. And I guess that it's even easier than the situation of the complex surfaces. But I really don't know. That it's a nice question, and I would be happy just to ask Anne Pichon for the moment. I never discussed with her this kind of story, because she really gave a nice answer for the curves, but then what to do with surfaces, no idea.
So, Lev, thank you very much for closing our mini course with this very nice talk. Thank you. So, let's break now.
Welcome back, everyone, to this morning session. It's a pleasure to be here again and give my last lecture to the fundamental singularities. And afterwards, James Damon will take over with his last lecture for the fundamental singularities. So, thank you for coming. I would like to take you back where we left off yesterday on my slides. So we were discussing a little bit the case of rational surface singularities and how the fundamental singularities work with this concept. Can we get that slide on the screen? Okay, this is a little bit more like hypothetical of art. Something more? Yeah, here we go. So, this was my summary of the theory of surfaces. And I'm supposed to talk about the topology. So, why did I do that here? Because we have the reduced memory that have the main observation is the positive one that you have to clear to the next. So today, let us see some other cases where the while so even for very simple linear that that all kinds of linear. So what do I mean by linear the IDS? This is step of this never the bottom step. Let's assume that this is a reading condition. That is verb, and then here's the condition. And then what does it mean? So that isolate again, so the numbers are fine, but I think what's more important for the problem is setup. Now here is the zero number difference, right? Hold the but nevertheless, the similarity is that first isolated with the transfer with the variety and then the transfer of the origin. It's not more than the data of so also referred to as this setting right here, we have the generic method right here, which is positive or status. So this is count for linear IDS, we have a linear embedded and it's a move it a bit to the side. There's not much more you can do about it. But eventually when the dimension of this too high compared to the photon dimension is all right. So yesterday, exercises briefly, we discussed the Turiner transform, and this can be used to get insight into the smoothings of some of these linear EIDS. So
the projection of the Turina transform. But if you're not so lucky, and we saw one example of this in the lecture yesterday, then maybe the exceptional set is even bigger, and maybe it even has bigger dimension than your original singularity, then the Turina transform becomes rather useless. So we have another bound on dimension for the Turina transform, and then you can just case by case try to study whether it has sufficiently nice properties or not. For instance, it can be, it can have non-isolated.
So here in this table, I try to summarize what we get out of this number.
-1, then you have a fat point singularity, right? So Turina transformation, it does not really make sense because you cannot take closure of something of the origin or things you usually do. But you have no problem because the Milnor fiber will also just be a bunch of points. And because the EIDS is Cohen-Macaulay, this number of points will be constant with multiplicity, counted with multiplicity, it will be constant throughout the deformation. So no problem to solve what the Milnor fiber looks like in that case. Then here, going one dimension up, you will have a curved singularity and it gets a little bit more interesting. So 2 by n matrices, maximal minors. Then in the Turina transform, this will look a little bit like this. So where do I draw this? The Turina transform will introduce a P1. So topologically, this is a sphere. And then the original singularity will consist of, I think, n lines. Yes. One example were the 3 coordinate axes in C3. And then you have just more lines stuck together in this bouquet of lines. And in the Turina transforms, these lines will be complex planes. And I can only draw them here as horns, but you have to imagine them as discs where I took the disc and I pulled it out a little to glue it here, right? So topological, this is 2 complex planes meeting transversally, but there's no way I can draw it in 3 real dimensions. I have to cheat a little bit. But topologically, the whole thing looks like this, with n of these horns. And then when you deform, what happens is that these pinch points, they open up, right? These are A1 curve singularities and they open up. So you get something that looks a little bit like Shrek, right? It has these ears. And I think Roberto also had this example in his thesis. So you can also pass through the Turina transform in that case. Okay, let's go back to the slides. Then here you have, homologically, you have a bouquet of S1s. In this case, here I had the case, the picture is for n equal 3. And it's a bouquet of 2 S1s. Where are they? Well, you can choose either 2 of these ends, and then the third one will be homological, the homological sum of the other two. So n minus 1 here. Okay, then next we can go to surfaces and higher dimension up to p less than 2n. And then we saw also in the example yesterday in the exercises that this Turiner transform is or can be interpreted as the total space of a certain vector bundle. And then depending on this dimension p, this vector bundle of a three-dimensional ISIS, then you would have a three-sphere in the Milnor fiber. It's really different here. So, and then from p greater than 2n and onwards, right, this is a 2 by n matrix, and then from this onwards, a linear EIDS has to be just a surjective linear map to the space of matrices, and there is not really anything that can happen anymore. So the Milnor fiber will just be homotopy equivalent to a point. Good, these were the 2 by n matrices. We can also take other matrix sizes. 3 by 4 is a case that can still be handled. This is a threefold singularity here. And it introduces a P2 as a central fiber in the Turiner transform, and then 10 A1 singularities. So more or less the same picture, only in different dimensions. And this example is, I think, in my paper with Anne Frübes-Krüger. And then from here onwards, it starts to get ugly. So 3 by 4 in, yeah, this is a surface singularity, and then here you have some non-isolated singularities, and that's where it really gets difficult to handle the situation. So I'm not sure what's coming out there. Questions? Good. Let's move on a little. So one thing that you have seen several times in this course, if you want to have a general machinery that always works for getting your hands on the topology of any smoothing, one thing you can do is you can do induction by taking hyperplane sections, right? You have a three-dimensional Milnor fiber, then you take hyperplane, hyperplane, and hyperplane until you eventually end up with a bunch of points, and then you try to reconstruct your Milnor fiber from these hyperplane sections. So usually what you prove for this is that there exists an open set of sufficiently well-behaved hyperplanes for any smoothing. So I'm stating this lemma rather vague because I think it has appeared in other lectures, and depending on your specific context, maybe you want to do some other choices, but you find examples of this in the literature frequently. So what you want to do is you want to make sure you have linear forms that define hyperplanes so that which are well behaved with respect to your singularity. So the hyperplane section should have singularities that are not worse than those of X, right? So if you took this cone here and you take a hyperplane section, then most probably you want to take a hyperplane section which also has isolated singularity here. And you don't want to take a hyperplane section that unfortunately happens to be tangent to your, right? So here could be a hyperplane section that's tangent. You don't want to avoid that. Singularities should not be worse. And then another thing that you usually want is that for every, when you smoothen, so you pass to t non-zero, and you have the
What I tried to draw here is, yeah, the more the picture of
image coordinate for the linear form. So again, you can go past to t non-zero, and you will have the yellow thing is this Milnor fiber of the original singularity, and in there you will have a smoothing of the hyperplane section, right? And then there are, you could also here just move this hyperplane a little to the side on the singular space. You would have this picture. So the hyperplane section will also be smooth in that case, and over the complex numbers it will even be homeomorphic to this hyperplane section, right? So in the real picture they differ, but in the complex they don't. And then you also have a kind of discriminant, which is the set of parameter pairs ut, so that the linear form has a critical point on the fiber over t, right? And the number of these critical points, that's the MD multiplicity. Did I say everything correct? I hope so. Otherwise, please correct me. Good. So what you can do with this is, as I said before, you can take hyperplane sections and try to recover your singularity from that. And then you have a theorem. This is more or less just standard Morse theory, that if you denote your hyperplane, the section of the, or the smoothing of the section by this MT transverse, then what's the difference between the section and the full Milnor fiber? Well, you attach some cells at the Morse points. And for smoothings of isolated singularities, this will always attach a cell of the same dimension of the as the Milnor fiber. So I try to draw a picture again. Here comes the hyperplane section. The M transverse are these two lines here. And now I start moving this hyperplane L, this hyperplane D, by varying the image number of the linear form L. I move it a little to the side until eventually I have a critical point of this linear form here on my Milnor fiber. And up to homotopy, what I attach is a half circle, right? And I attach it along these boundary points of the circle. And these boundary points have to go somewhere to here the hyperplane section, the smooth hyperplane section, some 2 points. So I could choose this and connect along some paths. This is only well defined up to homotopy, right? And the problem is really that it's extremely difficult to get your hands on where these attachments take place, right? And next week I will hopefully present to you some ideas on how you can do these computations, at least with computer, where these attachments take place. But I think there's very little recipe to keep track of this with pure theory. Good. So we may not be lucky and know all the topology of the Milnor fiber, but what we do get is a formula for the Euler characteristic. Because wherever these things attach, there's the Euler characteristic changes by 1 from every attachment. Or by +1 or -1, I should say. So if we reply this repeatedly, we eventually have a deformation of points, and then we can build up from that. And we get formulas like this, right? And you've seen these kind of formulas also in other occasions throughout this week. So the Euler characteristic of a smoothing is some alternate sum of polar multiplicities. Good. So which machine to use when you want to know more? And yeah, if you want to know more than this Euler characteristic, then at least for isolated singularities in a certain sense, you have more refined theorems where you can say where attachments take place, only that you have to do a little modification of the setup. So in the stratified sense. Isolated singularity in the stratified sense means the restriction of F to every stratum is a submersion, or has the to do with the function. It's totally independent of the function. That's So Mihai Tibar has already done a sketch of how this can be generalized to complete intersections with isolated singularities in a stratified sense. And then you get this kind of formula. So you start with F, a map from X to CK, and you have to take a little care of the details of how to define stratified, isolated, complete intersections. But if you want, just think of X as having an isolated singularity itself, and then it should be rather straightforward what it is, what this means for F to be isolated, complete intersection on X. And the formula is the Milnor fiber. It's homotopy equivalent to, I call this the complex link of codimension K, which is maybe, no, I think it's not an established term, but what I mean by that is the complex link of a singularity is you take the singularity and the generic hyperplane and you wiggle it a little bit to the side. For what I mean by complex link of codimension K is you take the singularity, you take a plane of codimension K plus 1, and you wiggle it a little to the side. All right? So this space appears here, and then you attach some suspensions of the usual complex links of X along the different strata. And these numbers, mu I, F here, they are kind of Milnor numbers in a Morse theoretic, from a Morse theoretic point of view. Okay, this is what I just said. All right, how am I doing with time? I think I have 15 minutes left, right? So maybe let's go a little quicker. So far, we have seen the T-bar's bouquet decomposition for functions with isolated singularities on a stratified space, and this is applicable to EIDS through a specific transformation, and we could call this the graph transformation. Let me go through this just quickly because I think it's enough for you to get the idea, and we will not check all the details here anyway. So how you start is you start with a defining matrix, and then you consider the graph, right? This has also appeared in Jim Damon's lectures yesterday for the K equivalence, I think. And then what you observe is that this graph, there are exactly m times n equations which define the graph in this product space here. And these m by n equations, they form a regular sequence on this space. Right? So you take the generic determinantal variety in the image and product with the domain. So I try to do a schematic picture of what happens here. And the key lemma is that the projection here to the y-axis, which is the space of matrices, but projection along the graph, right? So here the light blue. The formula. So you recognize this from the other one I showed before. And then the determinantal Milnor fiber is this complex link of higher codimension and a suspension of, or a bouquet of suspensions of the usual complex links of the generic determinantal varieties. Yeah, right. So this here up front, this is the intersection of the generic determinantal variety with the plane of codimension K in general position of the origin. And here, again, you get some numbers which are rather tedious to compute, but there were some examples in Dirk's lectures, at least for the hypersurface setting. Good. So for smoothable IDS, it takes a simpler form because there's only one set of one stratum where we have to take care of, right? So look at this formula, and let's go back 2 slides to compare it. Here's a double wedge sum, and the first one disappears when we have smoothable IDS, right? So the vanishing topology splits into a bouquet of spheres and this mysterious part, this complex link. And that's why I think the linear EIDS are of particular interest, because they will appear everywhere. This is independent of the matrix A, for the same reasons that the complex link in Mihai Tibar's formula was independent of the function f. So we still don't know what these complex links look like in general, but I think by now, if the referees agree, we have a good formula for the cohomology of these spaces. So my theorem here is that we have this this short exact sequence. So in the middle you have the cohomology of your Milnor fiber, and here you have something that is quite well understood. It's still complicated, but well understood. So what I have here is the cohomology ring of the Grassmannian of S-1 planes in M space. And one weird thing that I have to do is I have to truncate it, right? So I take cohomology ring of Grassmannian and imagine this as a filtered vector space in different cohomological degrees. And in degree D, I take a cut and I say, from this onwards, I forget what's there. So I have this sub-vector space. So the claim is that this embeds into the cohomology of the Milnor fiber, and the quotient is concentrated in degree D. Good. How do we arrive there? Well, here I have a kind of problem, I hope, that Jim Damon forgives me for that. I was hoping that he had covered parts of his characteristic cohomology already yesterday. And so I felt confident to recall the concept of characteristic cohomology. And now it will probably be a spoiler in some parts, but Jim Damon has some papers on this, and the rough idea is the following for hypersurfaces. So you have a map from CP to the square matrices, and here the determinant function, right? So the singularity, they sit in here like that. Over the central, over 0 here, you have the set of degenerate matrices, this generic determinantal variety, and then here your determinantal singularity as the preimage of that. And the same holds for the Milnor fibers, right? If you take the determinant equal to delta, you have here a generic determinantal Milnor fiber and the preimage of that. And this generic determinantal Milnor fiber, it's pretty well understood. It's topologically just SLMC. And then you can say the characteristic cohomology of this other Milnor, of this special Milnor fiber here is just the image of this pullback in cohomology, right? And this SLMC, just like Grassmannians, it has a very well understood structure of the cohomology, right? So as a vector space, this is just a graded exterior algebra. And I guess you will see more of this later today. And what I would like to discuss for the last 10 minutes, I think, is what is another related idea. I mean, this idea of having a universal object to pull back from and also do this in cohomology. This should also work for smoothable IDS in the following sense. So if we start with a map from CP here to Cm by n and the determinantal Milnor fiber, then observe that this determinantal Milnor fiber, it appears as the preimage of the generic determinantal variety. But when it's smoothable, then I can really restrict to the preimage of one stratum, because it's smoothable if and only if I can move the image of A away from the singular locus of the generic determinantal variety. So I can write this as the preimage of one stratum, and the idea that I would like to propose here is to take Jim Damon's setup and replace the generic Milnor fiber by this other universal object, that one stratum. And then you get similar output. So now it's a little more complicated here. You don't have the integers, but really cohomology rings of Grassmannians. Okay, and I don't expect you to fully understand the formula, and I don't have time to explain how to arrive there, but it's possible. And you may guess already that these cohomology rings of Grassmannians, that's really what appears in this other formula for the cohomology of complex links that I showed you before. So the cohomology ring of Grassmannians is generated by Chern classes of the tautological bundle. And what you can observe here is that when you are on this stratum, this is just the set of matrices of rank R. So every such matrix has an image vector space, there's a kernel vector space, and so on, right? So there are several natural vector bundles on this orbit. And what you get out of the proof of this proposition is that this subring here is generated by the Chern classes of the plug in the whole Milner fiber. And somehow magically, and this will also play a role in the lecture after this, I think, these eta, these generators of the Koszul algebra, they automatically seem to live in so high degree that if you have a smoothing, then they pull back to cohomology groups which have to be zero because of the Lefschetz hyperplane theorem. So they don't really play a role. And what remains is only this ring in the degree zero of the Koszul algebra. And then the question is, how does this ring pull back in the degrees which are less or equal to the dimension of the Milner fiber? And I have another theory, another story on that. So what's the time? I think I'm almost over, right? Yes. So maybe we skip this part, right? It's just to say. People might find is interesting. At some point, we were discussing this: do the generic determinantal varieties have Milner's property? And I think they don't. Usually, they don't. So the constant sheaf is not perverse for the middle perversity. All right, and that should be it. Thank you very much. Do we have time for questions, or should we switch to Jim Damon's lecture? Okay, are there any questions? Yes, let's get you a microphone.
In the formula for the Milner fiber, there is some influence on a few things. So if you look at it, yeah, that's good. They are not
Then you pass to a combination of F and the generic linear form, and this will have, say, this is the L axis and this is the F axis. Then this will have a bifurcation diagram, or this surf diagram, and then you get So welcome back after this short break. And it's a pleasure to have with us again Professor James Damon from University of North Carolina, who will present us the last of this lecture, the last talk of this lecture series on determinantal singularities. So thank you very much.
Okay, I just have to share my screen now. I'm trying to do it. Here we go. Okay, this is it. All right. Over here and you full screen mode. Okay. So it's a pleasure to be back here again. This seems to hopefully be working better than the first time I tried. I can see that Matthias gave you a good helping of the use of Lie group type methods in understanding nature of singularities. And I'm going to be continuing this from what I started last time. So let me just quickly emphasize 2 points. One, matrix singularities, as I said last time, although they're generally can be non-isolated singularities, they fit into 2 other classes of singularities obtained from some universal type and exceptional orbit variety of pre-homogeneous spaces. And these are going to be relevant for the goal of determining the topology of the singularities. And we want to do it both for the case of the Milnor fiber for a hypersurface singularity V and for the complementive link of in general, for general V. And so we're originally going to start doing this in the full generality of singularities of a given type. There are 2 contributions. We talked last time about the contribution from the topology of the germ F0 and how it interacts with V using various equivalence groups for this and relating the topology for the singular Milnor fiber with information about the deformation theory. What we're going to do today is talk about the contribution inherited from the topology of V, and then, to the extent possible, indicate how these 2 contributions combine to give the topology of V0. So the starting point for this is the notion of characteristic cohomology. Matthias mentioned that in one case, in what he's talking about, and I'm going to talk about it for the general case for singularities of type V. So I'll start with the case for Milnor fibers for a hypersurface V. So we'll let H from, V will be in C capital N, H will be a defining equation for it, and we can choose numbers sufficiently small, delta, epsilon, and eta, so that first of all, F0 is going to send the ball of radius epsilon into the ball of radius delta. And then we have 2 Milnor fibrations. The Milnor fibration for H here, and also the Milnor fibration for H composed with F0, which is basically the Milnor fibration for V0 in this case. And we can do this for both of these by choosing eta, delta, epsilon appropriately sufficiently small. So if we pick such a W inside of this this ball, this punctured ball, we have both the Milnor fiber for V, FW, and we also have the Milnor fiber for V0, which I'm going to call VW. And this condition where F0 takes the one ball to the other implies that when you restrict F0 to the Milnor fiber of V0, it maps to the Milnor fiber of V. So we can then pull back the cohomology of the Milnor fiber of V, and I'm going to denote this by A sub V, and this is going to be what I'm going to refer to as the characteristic subalgebra of the cohomology of the Milnor fiber. And I'll remark, it seems like we made a lot of choices, but in fact, this is independent up to Milnor fiber cohomology algebra isomorphism of all the choices. So as far as being a subalgebra of the Milnor fiber is cohomology, in some sense, this is intrinsic up to isomorphism. For complements and links, we can do a similar kind of thing. We know that we can find for general V, we can find a delta so that for delta prime smaller than delta, that the spheres about the origin are going to be transverse to V. And we can form a pair, the ball and the link of V in the sort of actually V inside the ball. And these are homeomorphic to the sphere on the ball and the link of V there. We can do this for epsilon prime less than epsilon for the case of V0. We can do the exact same thing. So then we again can choose epsilon prime and delta prime so that F0 takes the closed ball of epsilon prime into B delta prime. And then we get an induced manifold on cohomology, which is going to send the cohomology of the complement of V to the cohomology of the complement of V0. Again, there are choices involved, delta prime, epsilon prime. We can think of taking the inverse limit of this as these go to 0, these pullbacks, but these are basically kind of, in a sense, independent of delta prime and epsilon prime under appropriate isomorphisms. So we're going to call this the characteristic subalgebra of the complement. Strictly speaking, it's local cohomology. However, we can choose good local representatives for it and get the cohomology in actual space. The third is the characteristic cohomology for links. And here, I'm going to do something rather non-intuitive, but it turns out that, and this is more effective in capturing the cohomology of links than doing the more obvious thing. It's going to make use of Alexander duality for spaces in spheres. So we have our sphere and the link of V0 in the sphere. And Alexander duality in spheres, when you state it in an appropriate way, turns out to say that the cohomology of the link, dimension Q, is isomorphic to the homology, and this is reduced homology, reduced cohomology, to the complement, dimension 2n minus 2 minus Q. But now I'm going to do this over a field of characteristic 0. So this is isomorphic non-canonically via the Kronecker pairing to the cohomology in dimension 2n minus 2 minus Q of the complement. So we can combine this. There's a homotopy equivalence of the complement of V0 in the sphere into the complement of V0 in the ball, because when you do this, you're removing the point of the cone and it just contracts onto the space. And this is independent of epsilon prime less than epsilon. So we're going to define the characteristic cohomology of the link as follows. We take the reduced cohomology of the complement in delta prime. We pull back by F0 to get cohomology in here in the cohomology of the complement of V0. Then this is a homotopy equivalence, so we pull back by J epsilon star to get cohomology in here. This cohomology lies here, so now we just go the alpha inverse and we get over back to the cohomology of the link. So the definition of this characteristic cohomology of the link is this series, and again, it's going to be independent of epsilons and epsilon primes, and so we just take this limit. But again, it's well defined on sufficiently good choices for epsilon and epsilon prime. I'll make a remark. Both of A and C for the Milnor fiber and the complement are subalgebras. However, it is not true for B. It is only graded K subspace of the cohomology of the link. So what are the properties of this? Well, if you remember, I pointed out and emphasized the point that when you take singularities of type V, they're not just a class of singularities, they actually form a category. You have both objects and morphisms. And this characteristic cohomology is functorial for both AV and CV, for the Milnor fiber and the complement, for the category of singularities, for a fixed V. So if we fix V, look at all the singularities of that type, this is functorial. For BK in the link, it's not, and this is because of certain choices made in the Kronecker pairing. But there is a substitute, something called a relative Giesing homomorphism, which works. The second important property of it is the invariance. So on the space of nonlinear sections, remember last time we talked about KV equivalence, which induces an equivalence between the singularities or pullback singularities. But there's also this subgroup KH, which further preserves the Milnor fibers for V of a hypersurface. And now there's the following characterization here of invariance. It's the following. It says that for the Milnor fiber, again, it's going to be preserved under KH equivalence up to algebra isomorphism of the cohomology of the Milnor fibers. For the complement, it is going to be cohomology, this characteristic cohomology is preserved under KV equivalence, again, up to algebra isomorphism, the cohomology of the complement. And for the link, this is preserved under KV equivalence up to group isomorphism of the cohomology of the link. So let me suggest why I think the term characteristic cohomology is appropriate. And it is with, we think back to the way characteristic cohomology works for vector bundles. So we take a vector bundle from E to Y with a structure group G. So G, depending on type of vector bundle, may be any of the standard groups, the orthogonal group, unitary, symplectic, special orthogony, and so on. And vector bundles are classified by maps into the classifying space given by pulling back the canonical vector bundle over the classifying space. So for example, Matthias talked about the Grassmannian. The various Grassmannians turn out to be appropriate infinite dimensional Grassmannians turn out to be appropriate classifying spaces for ON, UN, and SPN. A key property is that if F prime is homotopic to F, it defines up to isomorphism in the same vector bundle. These classifying spaces have cohomology. They're frequently polynomial algebras. In most cases, there are no relations between the generators. So you can pull back these characteristic classes, and the classes you get are characteristic classes for the vector bundle, and they're functorial under pullback by G. So in a sense, these generate a, quote, characteristic subalgebra. And it's well known now how useful these properties are in the case, for example, if the vector bundle is the tangent bundle for capturing properties of the manifold. So in our case, what we have in place of BG, we have our variety V inside of Cn, and we pull back our maps. We're pulling back V instead, and instead of homotopy equivalence, we've got equivalence under these groups of equivalences, which are infinite dimensional groups. So a question then is for V, what are going to be the corresponding cohomologies for the Milnor fiber in the case of hypersurface case, complements and links? And then we can pull back these classes to get corresponding classes in the appropriate objects for the case of our V zeros. And this will generate the idea of a characteristic subalgebra, which I called A, B, and C, depending on the conditions. So in order to carry this out, we need to, in the case of these, be able to compute the cohomology in those three cases. And this is where I'm going to turn to illustrate this matrix singularities. And remembering that for matrix singularities, they're example of these, they're of exceptional orbit varieties of prehomogeneous spaces. So I'm going to generally let M denote whatever space we're talking about, and DM star will denote the singular variety of singular matrices in the three cases. And I'm going to do it for M by M. Matthias had already talked about some aspects of M times P. There's something that this also implies for that, but I'm just going to concentrate mainly on M by M. And the star up here can either be nothing for the general symmetric or skew symmetric in the case M is even. And the reduced defining equations H turn out to either be the determinant for the general and the symmetric, or the Pfaffian for the skew symmetric case with M even. So I'm going to simplify some notation just slightly. Strictly speaking, for each of these singular varieties, the characteristic cohomology would look something like this. And I'm just, in order to simplify notation, I'm just going to forget the DM and just put the stars up here. So it might be empty, SY or SK to indicate the corresponding here. And the other thing I'll say that I'm going to concentrate for the case of links, working with K with characteristic 0, but for the Milnor fiber and the complement, R can be any coefficient ring initially. We'll be more specific shortly. That's what I've just said down here. In the case of, in the symmetric case, there are really two important cases. One is where R is a field.
Sorry, could you say that again? Sorry, I'm having trouble hearing you.
Sorry, Sirius decided to talk to me. So anyway, there are two cases for the symmetric case, either a field characteristic 0 or for the Milnor fiber, the case of Z mod 2Z. So let's talk about this. So for exceptional orbit hypersurfaces, what is the strategy? Well, say for the Milnor fiber, we want to work with the local Milnor fiber. However, this does not work well if you want to have group actions. But it's true that for these cases, the local monofiber is diffeomorphic to the global monofiber. It's sort of a Morse argument proving that there's no extra anything contributed once you get beyond sufficiently small ball. The global monofiber now is actually a nice, smooth, complex analytic variety. And there's a group action, which is a subgroup of the group that we get for defining the exceptional orbit hypersurface, which acts transitively on it, so that this is holomorphically diffeomorphic to a homogeneous space G prime mod H prime, both of linear algebraic groups. Now, these linear algebraic groups have maximal compact subgroups. And in fact, this homogeneous space G prime mod H prime is homotopy equivalent to the corresponding quotient of the maximal compact subgroups. And we can think of this here as yielding a compact model for the monofiber. And this is going to play a key role in understanding the topology. So this is for hypersurface. For exceptional orbit varieties, where it's not a hypersurface, it is still true that you can carry out the same decomposition for the complement, and you obtain a compact model for the complement. So that's even true in the non-hypersurface case. And we're going to use three, especially three, to compute the cohomology and even the homotopy groups of the Milnor fiber for the case of these matrix singularities. And for four, we'll be able to do it for the complement and the link. And one of the consequences is it turns out that in quite contrast with the case of isolated hypersurface singularities, that the Milnor fibration is cohomologically trivial as far as the monoderivative is concerned as a result of this. So here's the first result. So let's take the global Milnor fibers of these determinant hypersurfaces. I said they're homogeneous spaces. So here are, it turns out that although we're thinking of three classes, namely general, symmetric, and skew symmetric, it turns out when we look at the cohomology, it actually breaks up into four classes here. And the symmetric case, there are different results depending on whether M is even or odd or even in this case. The Milnor fiber looks the same for both of those cases. So this is what the Milnor fiber looks like as these homogeneous spaces. These are quotients of linear algebraic groups. They have the maximal, so for example, here, the maximal compact subgroup of SLM is SUM, and for SOMC is just SO. So in fact, this Milnor fiber is homotopy equivalent to this quotient here, in the same way in the other cases. Now, it's a very nice fact that these all happen to be symmetric spaces in the sense of Cartan. And their cohomology, it's much easier to compute the cohomology for these than it is to compute for just an arbitrary homogeneous space. And in fact, the cohomology, which has been computed, is actually given by the formulas over here. So we're actually able to say for the case of, now this is the case of the determinant of hypersurfaces. This is not matrix singularities yet. This is just the determinant of hypersurfaces. This is what the cohomology is. Notice the cohomology in 3 of the 4 cases are exterior algebras instead of generators. And in one case, it's a module in 2 elements over these. These generators turned out to have a nice relation with characteristic classes for vector bundles. In fact, there's a notion of transgression from these. And in fact, these transgress to certain characteristic classes for vector bundles. So we think of these as in some sense being the characteristic classes for the matrix singularities of each of these types. In the skew symmetric case, and we can replace. So although I did this for a field of characteristic 0, in fact, these formulas hold true in both the skew symmetric and general case using z coefficients, and hence basically for any. Well, in the symmetric case, when this is for characteristic 0 here, but if we go down to characteristic 2, then it turns out that it's an exterior algebra on these generators E203EM. And a really interesting point, I think, is that here we're talking about complex singularities, And when you look at characteristic 2, it turns out these E sub i's are Stiefel-Whitney classes for a certain vector bundle which lies on the, it's a real vector bundle which lies on the Milnor fibers. So this is kind of, you know, when you have results where things are in terms of bouquets of spheres, you have a certain perspective on it. Well, here this perspective is sort of thrown off quite a bit when you realize that these other features start entering into cohomology of Milnor fibers. For the cohomology of the complements and links, we have the following results. So here, again, I said the complement can be written as a homogeneous space. Notice this time, instead of SLN, this group is the full group that we use to define the pre-homogeneous space. And it is, in this case, we get for the symmetric case, it's OMC divided by OMC. And again, it has its homotopy equivalent to a quotient of maximal compact subgroups. And the same thing for, and in the case, it's really easy to see it in the case of the general matrices, because when you take the determinant 1, all you're getting is just the group UM. And similarly for the skew symmetric case. Now, we can compute the cohomology of the complement, which is the cohomology of this, the quotient of the maximal compact subgroups. And again, in this case, it turns out in all 4 cases, these are exterior algebras on this set of generators. What happens to get the link? Well, because of the way I define the cohomology of the link, we're using Alexander duality starting from the cohomology of the complement. You get it as follows. You take these classes, let me see if there's, all right, that's not, let me, you take these classes, you upper truncate, take off the very top dimensional class, and you shift it by this amount. And this gives you the cohomology of the link, which is sort of interesting because these links are highly singular real analytic spaces. They're not manifolds. And this is what the cohomology of these links are going to look like when this is shifted. The algebra structure is not there in the link. As I said, you lose the algebra structure, but this gives you what the characteristic, this gives you what the cohomology is for a link. Again, this is just in the universal case. And so now what we want to do is to try to bring into the question actual matrix singularities here. So the way we're going to do this, we have these compact models coming from the both in the Milnor fiber and in the complement, coming from these the quotients of these compact maximal compact subgroups. So what we're going to define in the case of the Milnor fiber, the idea of a vanishing compact model for it, where we're going to take the compact model we have in one Milnor fiber and basically make it part of a family of compact models which continue on as the radius of the ball goes to 0. So it's going to be a family. So it's going to be a compact space. We're going to have smooth curves in the target, and also a smooth curve here for this is going to be the radius of the ball, and this is going to be a mapping which goes into the Milnor fibration here, so that if we restrict to this equal to t for a particular value, the smaller ball in both the source and the target, this is again a Milnor fibration for h. And furthermore, for each value of t, this is going to map into one of the Milnor fibers lying over this point gamma of t, so that this is a homotopy equivalence. In the case this is a Milnor fiber. So what we have is then, if you think of it, it's just like the family of vanishing cycles. This is a family of vanishing compact models. There's a corresponding way to do this in the case of the complement, where now you want a family of these compact models that shrink down inside the ball as the radius of the ball gets smaller and smaller. And this family is going to be in the complement. Again, we saw there are compact models for one, and we're going to extend it to a whole family. So what are the purpose of these compact models? It's going to be to detect the non-vanishing of this characteristic cohomology when we pull back the cohomology from the universal case to the individual Milnor fibers. So if we take a graded subgroup of this compact model, we say it's detected by a compact subspace Q sub E if, when we pull back the cohomology, induce an isomorphism from E onto the cohomology of this space. So what we're going to try to do in order to detect this, we're going to use these ideas of detecting the groups within the compact models using the vanishing compact models. So we say that an embedding from CS to CN detects E. So now we're going to talk about Milner fibers now. If, again, for these sufficiently small numbers, eta less than or equal to epsilon less than delta, there is a vanishing compact model for the Milner fiber of H composed with IE now. So H is on here. So the same thing is true. This is going to be a vanishing compact model for this Milner fiber. And furthermore, so that this equation holds true, what the equation is basically saying is that the way I detect E and compose it with the image of this QV into the Milner fiber is the same as taking this for a particular value into this Milner fiber and then composing with the inclusion map into the Milner fiber. So when you have this holding true, a consequence is a detection lemma for the Milner fibers. So if F0 defines a singularity of type V, if GS from CS into CN satisfies when F0 composed with G is K equivalent to a germ detecting E, then this characteristic cohomology of F0 contains this graded subgroup, which is isomorphic to E via this pullback map. So essentially what this is doing, it basically says, look, this composition here, when we pull back by G, we're already going to detect E. So by the functoriality characteristic cohomology, that copy of that E has to already exist in the intermediate space, namely the variety defined by F0. There's a corresponding result. Let me see if I said this. There's a corresponding result for, if you see at the bottom of the screen, for complements and links that I won't bother specifying, but this gives you the idea. So in order to do this, so I gave you an abstract compact model for the Milner fibers and for complements, but it's abstract. It's not actually sitting inside the spaces themselves. So there's a way to do this to actually get models inside the actual Milner fibers. And this is using it, pointing out that these things are symmetric spaces. And there's something called the Cartan model for a symmetric space. When you represent a symmetric space as a group divided out by a subgroup, which is invariant under an involution, there's a way of mapping the symmetric space, which are going to show something called C, inside the group itself, which sends G to this involution times G inverse, sending G to sigma times sigma inverse. We can do this for all three of our cases. It turns out for SUN, for the general case, we can just let G be its own Cartan model. That's fine, because that's a symmetric space. For the symmetric case, for SUN or SOM, it turns out sigma happens to be taking something to its complex conjugate. And the Cartan model happens to be, in this case, the intersection of SUM with the symmetric M by M symmetric matrices. And in the case that we take the skew symmetric case of SUM over SPN, in this case, the involution turns out to be multiplying the complex conjugate on one side by J and the other side by J and inverse, where these are kind of canonical two M by M skew symmetric matrices formed by SIG 2 by 2 n blocks of 2 by 2 skew symmetric matrices on the diagonal. And its Cartan model turns out to be what we have here by intersecting SUM with SKN and multiplying by on the side by JN inverse. So there's a theorem which says that if we use these Cartan models, that you can actually decompose these compact models, giving a type of Schubert decomposition. So I'm not sure to what extent Matthias got into talking about Schubert decompositions, but these are generally done for like Grassmannians. But in fact, it turns out there's a way of having Schubert decomposition for these compact models and even extend it to the Milner fibers. And these Schubert decompositions, which are cell decompositions, can be identified by the Kronecker pairing with the actual cohomology generators. So this gives us a way of actually seeing geometrically where these cohomology generators are in the compact models. So here is the overall scheme of where we are. We have the Milnor fibers in the cases. We have their corresponding representation as quotient spaces, homogeneous spaces. There's the corresponding symmetric spaces. And then there's the compact model. So here's the Cartan model. The Cartan model gives us just the compact model for the general case. For the skew the symmetric case, it gives us this compact model. For the skew symmetric case, we can just multiply by GAN. That's still going to keep that's not going to change the topology. And we get this compact model. So these are compact models in the Milnor fibers for the Milnor fibers. So with these compact models, it's actually, in a naive sense, very easy to construct vanishing compact models. All we do is take these models which are in there and just multiply by T, and they're going to shrink down. And furthermore, and this is in both the Milnor fiber and the complement, this works. And furthermore, there's a way of defining detection maps using a lower dimensional Milnor fiber and a higher dimensional Milnor fiber for the compact models. And these actually, when you do this, this actually will detect from here the cohomology that's actually given by this space right here. So we have these ingredients now. We have vanishing compact models. We have a way to detect it. We have vanishing compact models for all the matrix singularities, and we have a way of detecting these. So what we want to do is put these ingredients together now for a more general matrix singularity to talk about what we can say about how much of the characteristic cohomology is non-vanishing. So we do this through kind of an odd thing, which in this case, and I'm going to give one way of doing this, mainly because, you know, as even in the case of characteristic classes for vector bundles, there are various ways of showing characteristic classes don't vanish. Here is one way in which we can see that the characteristic cohomology doesn't vanish for matrix singularities. So what we're going to do is we're going to take a standard flag of subspaces, and we're going to form what's called a kite space of size L. So this, for any of the general or symmetric matrices, what we're going to have is a subspace of matrices of this form. Every place there's a star is going to be a general entry, and then stars down a diagonal. And in this case, it's either a general matrix, or in the symmetric case, it's going to be a symmetric matrix. This subspace maps into the space of matrices. And this is going to be something which detects the characteristic cohomology coming from part of the total characteristic cohomology. Because these properties of characteristic cohomology are invariant for the Milnor fiber, say under H equivalence, we can take kind of the H version of the group equivalence, and as long as we change the mapping by anything in this orbit, we again are going to have the same detection properties, the same things. So I'm going to refer to this as an unfurled kite map. In the skew symmetric case, we've got to change it slightly because we need skew symmetric matrices. So if L is even, we can have an L by L skew symmetric block here. But down here, instead of single entries on a diagonal, we need these 2 by 2. We need these 2 by 2 blocks like this going down the diagonal. And these can be arbitrary. Again, these can be arbitrary non-zero entries here. And this is going to be, actually, these can be arbitrary because we're not in a group situation. These can be arbitrary, and these can be arbitrary. And then you have a corresponding skew symmetric kite maps here, and this corresponding unfoldings. So here's some example. Here's an example. Here's a linear kite map of size 4 into the 5 by 5 general matrices. And the second example, this thing, now this does not at all look like the kind of example I talked about, but here is what happens if you take a 3 by 3 kite map and you can perform row and columns operations on it, just the way you do with matrices, but using elements in the local ring to get other elements, and this gives you a quote unfurled kite map. So you have a lot of flexibility in the form that these things, which are going to detect singularities, can take as a result of this ability to perform this KV or KH equivalence depending on the situation. So the result then, so here's what we can say when we have a matrix singularity of one of the three types. So suppose we have for this F0 that when we can restrict it to a subspace, and that we get what is effectively the composition of F0 with one of these unfurled kite maps here. Okay, then the detection result says that we are going to detect cohomology in the Milnor fiber or of F0 that we would also see that we would get from G here. So in particular, what happens for general matrices, if you have that it contains a kite map of size L, that the cohomology of the Milnor fiber actually contains this entire exterior algebra. And this is for the matrix singularity, not for the universal case. For skew symmetric matrices, where we want both M and L to be even, you get a corresponding exterior algebra. For symmetric matrices, you get two cases. In the case where we take a field of characteristic 0, you're going to get an exterior algebra, and this SL here is either 1 or 3, depending on whether L is even or odd, characteristic 0. And if you look at the cohomology, characteristic cohomology, Z mod T Z coefficients, you get an exterior algebra on these elements. And furthermore, these elements, as I said, are Stiefel-Whitney classes of a certain pullback of a vector bundle. So interestingly, you get a lot of characteristic cohomology, even in characteristic 2, for the symmetric case. And this is somewhat analogous to what happens with real vector bundles when you use Stiefel-Whitney classes. For the complements and links, we get an analogous result. So let me just, if I can go through here. So if again, we take a matrix singularity of any of the three types. So suppose it contains a kite map of size L. Then, first of all, the complement contains an exterior algebra given by this table right here. Okay. And the link, it contains a graded vector space that we obtain as follows. So this is a result of Alexander duality. We take these exterior algebras, we upper truncate it. That is, we take away the top term, and then we shift it by this amount. So again, we're going to get this, and when we shift it, we've lost the algebra structure, but we do have all the cohomology sitting in that we have from here. So, so this is the form it takes when we have this kite map. So let me go back to the examples. So if we go back, take a matrix singularity of this form, 5 by 5 general matrices, and suppose just say we have it like this, and it has the property that when y1 through y4 is 0, all these g's vanishes. Then, when the y's are 0, we're getting a kite map of size 4. So by the theorems, we can say that basically, independent of what the g's are here, we are guaranteed that there's a certain amount of cohomology that's going to be present in the Milnor fiber for this case. So, so we have, and also for the complement and for the link. So, so notice that these, even for these matrix scenarios, are far from looking like bouquets of spheres anymore because of this exterior algebra structure and Milnor fiber cohomology. The one thing I'll point out for the link, in this case, let's see, how am I doing here? I just want to double check time. Okay, 10:15. I think I started just a few minutes late, so let me just quickly finish up these examples. In this case, notice what this says is you take the highest dimensional thing here, which is the product of all four, and you delete that. So what's the next highest thing? It's E3 times E5 times E7. That has dimension 15. You shift by degree 24. That gives you something 39. So there's a 39-dimensional class. How does that compare with the actual geometry of this? Well, when you pull back the hypersurface here in M5, you're getting a 20-dimensional complex hypersurface. It's 40-dimensional real. So when you intersect with the sphere to get a link, you get a 39-dimensional real analytic set. This, in the characteristic cohomology, is the generator of the fundamental class of that. So it shows you how characteristic cohomology can be very intricately related with the cohomology. And in fact, what's interesting here, if you actually look at all these numbers, in fact, in every dimension except for 2, you get non-zero you'll get non-zero cohomology in the link. So it's incredible. It tells you how complicated this is, and the same way with these others. In the symmetric case, as I said, in this case, if we let y1 and y2 be 0, we get this unfurled kite map. But it's still a kite map of size 3. So in fact, we can say that we have this cohomology for the Milnor fiber, the complement, and the link. And again, if you do the same calculation I did before over there, for this, the top class is going to be, after you truncate it, is E5 shifted by 10, so it's 15 degree. That is, again, the fundamental, dual fundamental cohomology class to the fundamental class for the real analytic set inside of the link here. Okay, so let me conclude now by bringing up some questions, okay? Namely, we've got two things. In the beginning part, we talked about the singular Milnor fiber, and now we're talking here about the cohomology, the actual Milnor fiber. Everything I said is the actual Milnor fiber of these highly non-isolated singularities. So what does the cohomology of the Milnor fiber look like? Okay, so we have this characteristic. Actually, I'm sorry. This is the singular Milnor fiber again. We have the characteristic cohomology. It's the Milnor fiber. We have the characteristic cohomology in the Milnor fiber. This is the Milnor fiber. But we can have another contribution. If we're in a field of characteristic 0, we can think of this as a direct summand. And the question is, in the Milnor fiber, what does this consist of? So we can ask several questions about this. So number one, from the singular Milnor fiber, we had a certain contribution which lies in dimension n-1. Question, does this appear as a summand in this thing right here? Secondly, in this thing, does it consist of more than just what we get from the singular Milnor fiber in this case? That is, does this vanish below degree n-1? And if one holds, can there be further additional contributions to this besides just what we got from the singular Milnor fiber? And fourthly, if 2 does not hold, where this is below this top dimension, can it be written as a submodule of this? So these are all questions which actually are fairly subtle. There is a way of guaranteeing that one holds if in some sense we can retract the smooth Milnor fiber onto the singular Milnor fiber. In that case, it'll guarantee that this is present inside here. As far as the others are concerned, as far as matrix singularities, it's basically wide open. But where there is some information to this occurs not for matrix singularities, but for hyperplane arrangements. And in fact, for the coordinate hyperplane arrangement, when you take a linear or nonlinear mapping of it, you're getting what's called a generic hyperplane arrangement or a generic hypersurface arrangement. And in this case, there have been some results by Orlick and Randall and Libgaber and Dan Cohen and Agsusiu, which basically say that in this case, all of this for the case there where V is this coordinate hyperplane thing, all this cohomology is there, and up here you not only get this part of it, but you get more. And this comes from the fact that for the singular Milnor fiber, you're deforming the singularities in the singular Milnor fiber, and it creates more topology here. So this gives you just an idea of just how wide open this is and how little we know except in a few isolated cases. For matrix singularities, some of the questions are for monomial classes outside of those detected, which ones still map to non-zero elements? It really involves looking carefully at the Schubert cell decomposition and understanding how these are going to capture classes in the matrix singularities. How about outside the cohomology of the link? What happens there, and does the Leham role play a role in capturing what's outside of here? And finally, for the symmetric case with Z mod 2Z coefficients, what are the non-vanishing Stiefel-Whitney classes of this vector bundle that plays a significant role for the Z mod 2Z cohomology? Anyway, if any of this is interesting, there are just incredible number of open questions where we know very little. And I think what we're doing here is just scratching the surface of what there is. So thank you for listening to this. I hope you found it of interest. All done. There we go.
So thank you very much for this nice talk. Are there any questions or comments? Yes, please, Terry.
I was wondering about the invariance of the characteristic cohomology. So you have an invariance theorem relating to the action of the groups.
Mm-hmm.
Supposing instead we had a family of smoothable singularities, which were coming from the n by n general determinantal case, and the family is Whitney equisingular. Can you say anything about the characteristic cohomology there? Is it fixed, or does it change, or what happens?
Oh yeah. So what I didn't say, in fact, I kind of point out in paper, is that if instead, so Whitney equisingularity, I think, will imply that these are topologically KH constant. If that's true, then in fact what I said is actually, when I invariance, I didn't say it, but it's actually true for topological KV or KH equivalents. So even under topological equivalents, these characteristic cohomology algebras are preserved.
And then the other question I had was in the formula for one of your last slides. Yeah, I think actually it's the formula maybe for the next to the last slide. You had this direct sum decomposition of the cohomology of the Milnor fiber.
Oh yeah. Let me do this. Yeah. So this is the Milnor fiber, and this is a really wide open question basically.
I was just wondering if you could. There's an intersection between your talk and Mateus's talk. If you work in the case of n by n determinantal singularities, can you relate this formula to his talk?
I'd have to think carefully about that because I don't know off the top of my head.
Okay.
Yeah. I mean, this is I don't know the answer to. Basically, I basically told you what I know just right now as far as the properties of this decomposition. And as I said, it turns out that for hyperplane arrangements, we understand more about this from work people have done. They didn't refer to it as characteristic cohomology, but when you interpret their results this way, you can see exactly what they're saying about this decomposition. But for matrix singularities, it's still very much an open question, the nature of this W, the complement to that.
Thank you.
Sure.
Okay, further questions? Maybe I also have a question.
Sure, Matthias.
So for developing the vanishing compact models of your universal Milnor fibers, you were considering them as homogeneous spaces, or you had linear groups acting on them?
Yes.
Or quotients of linear groups, right?
Yes.
So the generators of your Koszul algebras, they are coming from these groups, and then there's also a classifying space for these groups and associated vector bundles on them, right?
Yeah. So let me emphasize though, but these are not just groups in general. These are actually quotients of groups. They're actually symmetric spaces. And that's different than just having the cohomology of the groups themselves. So there's a point there. I mean, the fact that these have this form in general, if you have a homogeneous space, there's formulas for how to write down the de Rham cohomology in terms of certain Lie algebra invariant things. But in general, it's not quite so easy. But in this case, because they're symmetric spaces, they have these especially nice properties, which allow us to say so much more than you can for just an arbitrary homogeneous space. I think that's a crucial point here.
Okay.
I don't know whether that answers your question or responds to your question, but they're not groups. It's the crucial thing is that they're symmetric spaces that play such an important role.
Okay. Well, further comments, remarks, questions? Okay, this does not seem to be the case, so let's thank Professor Jim Damon again for the 2 talks. And I think this is also the last talk of this school, right?
Yes.
So you want to say some words?
Yes. Okay, thanks. Professor Jim,
Yes.
thanks a lot for your contribution and for all the time that you have spent for preparation the course. We want to thank you very much for everything. Okay. And also, I want to suggest all the team of lecture that is here with us to come this way to take a photo with Professor Jim. There, could you come here, please? Maybe we could invite also the student to join us. Why not? Reinaldo, você acha que daria para tirar uma foto com o time de professores e os alunos também? Please come the student as well, please. Stay here. Acho que talvez Reinaldo possa falar como pode ficar melhor para as expor em linha. Come. Just one step. Good. Come, please. Two rows. Okay. Maybe
Closer together, I think, right? Closer.
Yeah.
You have to be at least there with the speaker, right? So, please.
Isso aí, ok. Vamos para cá, vamos passando lá. Okay, vamos lá na frente para ele ter ângulo. Vai lá. Ok? Dá para pegar todo mundo? Ok? Sem máscara ou com máscaras?
Ok.
Você pode tirar rapidinho? Ok, sem máscara rapidinho. 1, 2, 3. Vai.
Okay.
Mede a respiração. Vem, Ana, rápido. Só um momentinho, vem, Ana. Sai na foto aqui do... Vai lá. Ok. Ok? Okay. Thanks a lot.
Okay. Oh, well.
Professor Jim as well, right?
Thank you. If you can hear me, I just want to thank all of you.
Hey, thanks, Professor Jim.
For all of your patience in working with me and getting this online thing to work. And for, I'm sure I'm missing a tremendous conference, and I so have enjoyed over the years all these conferences at San Carlos with the wonderful hospitality there. And I hope it's in future time I may still make a future conference.
All right. Okay. Thanks a lot.
Good seeing you, Matthias and Terry. Hope you guys had a great time there.
Okay. Thanks.
Thank you.
Bye-bye. Thank you very much. Bye. So my last thanks. So thanks for all the students for coming. And it was a big pleasure to have all of you with us this time. And also, thanks for the team of lecture for the preparation, the time that you have spent with all of these things. Very nice material, very good material. It will be available for all the students. And special thanks to Professor Mihai Tiba, who idealized the idea of the CIMPA school some time ago. And he was, trying to push all of us during all the pandemic time to keep the idea of the school. And we were able to do online version in 2021 with the help of Anne Schubert. Thanks for her also. And this in-person version, we were expecting to have Mihai presence here, but unfortunately, he could not come. But I want to register that we are very thankful. We are very thankful for him because of all his efforts and work to keep the idea of this CIMPA school. Okay, let's thank him, please. All right, now it's time to finish, and thank you all of you very much, and also special thanks for event section and all the ICMC team, Paulinho and Leonardo from the IT desk. Okay, thanks for a lot of him. And if in the case that you stay for the workshop, of course there will be one more week ahead. And see you. Thanks. See you next time.